Calculate the compressor horsepower required for an adiabatic compression of 80 million standard cubic feet per day gas with inlet temperature of 70 degrees Fahrenheit and 800 psi pressure. The discharge pressure is 1400 psia. Assume the compressibility factor, absorption and discharge conditions to be Z1 equal to 0.95 and Z2 equal to 0.8 respectively, and the adiabatic expansion is equal to 1.3. Adiabatic expansion, adiabatic exponents is equal to 1.3 with adiabatic efficiency of 0.8. If the mechanical efficiency of the compressor driver is 0.94, what is the brake horsepower required? Also calculate what BHP is required. Also calculate the outlet temperature of the gas. Now, the given information is okay. Now, let me write down the given data. The flow rate is 80 million standard cubic feet per day, while the inlet temperature T1 is 70 degrees Fahrenheit, which is 530 degree Rankine. Now we have U1 to be 800 psia and the discharge pressure to be 1400 psia. Z1 is 0.95, Z2 is 0.88. It's 1.3. Why this is adiabatic, right? The mechanical efficiency 0.94. Now let's make use of the horsepower formula to calculate the horsepower formula for calculating compressor horsepower. Now we use 0.0857 times gamma divided by gamma minus 1 and the flow rate times the inlet temperature times the average compressibility factor times 1 over the adiabatic efficiency bracket open P2 divided by P1 raised to minus 1 divided by gamma minus 1. So we have 0.0857 times 1.3 divided by 0.3 times 80 times temperature 530 times 0.95 plus 0.88 divided by 2 times 1 over 0.18 1400 divided by 800 raised to power 0.3 divided by 1.3 minus 1. Now, let's calculate the horsepower here. Let me view our calculator. Zero point 0857 times 1.3 divided by 0.3 times 80 times 530 times 0.95 plus 0.88 divided by 2 times 1 divided by 0.18 times bracket open bracket open 1 0 0 divided by 8 0 raised to power 0.3 divided by 1.3 minus 1. So this will give us 2422 horsepower. So this is the horsepower. Now to calculate the BHP, V is equals to the horsepower divided by mechanical efficiency, which is the horsepower is 2422 divided by 0.94. 0.94 2576. Okay, 77. Let me see. Okay, we also need to calculate the outlet temperature. Now, we also know that the adiabatic efficiency is something as the outlet temperature, the adiabatic outlet temperature minus the inlet temperature divided by the actual outlet temperature minus the inlet temperature. This is equal to adiabatic efficiency. So now to get the outlet temperature, we now say we can rewrite this equation to be T2 minus T1 equal to 1 all over adiabatic efficiency times T2x minus T1. Now this is the outlet temperature for an adiabatic expression, for an adiabatic process. So now to get this T2x, now we are going to employ what we call the ideal gas equation. So now for an ideal gas equation, we know that P2 V2 divided by T2x Z2 is equal to P2 is equal to P1 V1 over Z1 T1. Now this also implies that V2 V1 is equal to P1 P2 times Z2 T2x divided by Z1 T1. Now we also know that going to adiabatic, the relationship between pressure and volume for an adiabatic process is PV P times V raised to power gamma equal to a constant. So P2 V2 gamma is equal to P1 V1 raised to power gamma. So now we have V2 over V1 all raised to power gamma equal to P1 over P2. Now that means V2 over V1 is something as P1 over P2 all raised to power 1 all over gamma. So this is the same thing as saying P1 over P2 over P1 all raised to power minus 1 all raised to power 1 all over y is same thing as saying P2 over P1 all raised to power minus 1 all over gamma. So now we have gotten this to be this. So now let's call this equation 1, equation 2. So now V2 over V1 is equal to what? Equation 1 is equal to P1 over P2 times Z2 T2x all over Z1 T1 equal to this again, which is V2 over V1. That is V2 over to V1 equal to this. So it's equal to P2 all over P1 raised to power minus 1 all over gamma. Now that means P1 all over P2 times Z2 T2 T2s divided by Z1 T1 is equal to what? P2 P1 all raised to power minus 1 all over. Now, if you move this to this other side, you have Z2 T2x divided by Z1 T1, which will give us P2 over P1 times P2 over P1 all raised to 1 over minus 1. So this will give us P2 over P1 raised to power 1 minus 1 over gamma, which is something as P2 over P1 raised to power gamma minus 1 divided by gamma. Now, from this expression, it now means that T2x is equal to Z1 T1 divided by Z2 times P2 divided by P1 all raised to power gamma minus 1 divided by gamma. Now, I've gotten this. So now we're going to substitute it into this equation. So we are going to have into this equation here, we're going to have our T2 will now be equal to T1 times Z1 divided by Z2 bracket P2 divided by P1 raised to power 1 minus 1 gamma minus 1 divided by gamma. Now minus T1 minus T1, look at it here. Minus T1 now here, this one now, the whole of this will be divided by adiabatic efficiency, then plus T1. So this is the formula to get our T2. So that means our T2 will now be equal to 1 all over adiabatic efficiency times T1 times Z1 all over Z2 bracket open P1 divided P2 divided by P1 raised to power gamma minus 1 raised to power 1 minus 1, then plus T1. Plus T1. So we have adiabatic efficiency to be 0.82. The inlet temperature to be 520. 520. Okay, 530, sorry. The Z1, Z2, Z1, Z2, Z3, Z1, Z2, Z1 0.95 divided by Z2 0.88. Now we have the discharge to be 1400 divided by 800 raised to power 0.3 divided by 1.3 minus 1. Then plus 580. Now let's calculate. Divided by 0.82 times 530 times 0.95 divided by 0.88 times 14 divided by 8 raised to power 0.3 divided by 1.3 minus 1. Plus 530. So the 626.2 degree Rankine, which is equal to minus 460 minus what I 626.2 minus 460 equal to 166.2 degree Fahrenheit. So this is the final answer. Thank you for watching to the end. Do wait to subscribe to my channel so that when next time I make new videos, you'll be the first to watch it. Thank you and God bless.